Welcome everyone once again for Photonics for Quantum 2. I'm Don Feiger, I'm your host, and we have an exciting talk today, almost finishing up a very full week. And before I introduce the speaker, I wanted to thank our sponsors whose logos surround me. And due to their generous contributions, we're able to deliver this content free to you, live and also recorded. If you want to hear the talks afterwards, go to the PFQ2 webpage, look at the program and click on the talk you want to hear. And you can see the video link at the drop-down box and the slides. Let's see, for tomorrow, I just wanted to give you a reminder. We have a talk from Dirk England and also a sponsor talk. So be sure to join us a few minutes early tomorrow. And now with no further ado, I introduce today's speaker, Lukas Chrostowski from University of British Columbia. Lukas, go ahead and take it away. And Lukas said he's fine if you ask him questions during the talk. He'll attempt to answer them in real time, or if not, just type them in at the end. Lukas, there are no hard stops, so you can feel free to go as long as you like. We have no poster presentation, so technically we have a whole hour.
Wonderful. Well, thank you very much, Don. Really appreciate having me give a talk here. And good afternoon and good morning to everyone. So let me just share my screen here so you can see my slides. And okay.
I can see your slide.
Wonderful. So I'm going to be speaking today about my work in silicon photonics and my recent entry into the quantum computing field via collaboration focused on coupling silicon photonics to electron spins in atoms. So I'm a professor at the University of British Columbia in Vancouver, Canada. We have funding from the federal government from NSERC. We have a silicon photonics program called SciEpic. And we also have a quantum computing program that just got funded a couple months ago. So we're going to be rolling that out soon. And I'm also with the Quantum Matter Institute. So just to give you a sense of where we're going for the next 7 years, we're establishing a software and a hardware training program in quantum computing. And a small portion of that program is going to be focused on silicon photonics, but there's a whole bunch of other stuff like superconducting and other approaches for quantum computing. So you can find out more at the Quantum BC webpage if you're interested. So the work I'm going to be discussing today is primarily from the people shown in this picture here. So I'm collaborating very closely with Professor Jeff Young in physics at UBC and Robert Rosendorf. We have a group of students, postdocs, and researchers here. And we also collaborate with the group of Stephanie Simmons and Mike Thewelt at Simon Fraser University, also in Vancouver. So here's the summary of what we're trying to do. Hopefully it'll take us less than 5 years or so to get to this picture. But essentially the idea is that we want to combine silicon photonics with all the gradient couplers and waveguides and large scale integration with photonic crystals and come up with a way of coupling to a single selenium atom. And I'll talk about this a little bit further in the presentation, that these atoms have really beautiful spin properties and make them really ideal candidates for quantum information processing. And the silicon photonics, as you'll see, is going to be a little bit more challenging because the wavelength we're operating at for these selenium atoms is not your standard telecommunications wavelengths. So this proposal was written by Stephanie's group. It was published in 2017, and this was essentially a proposal of let's try to build this structure, and I'll give you a description of where we're at today. So here's an outline for the presentation. So I want to provide a little bit of introduction to silicon photonics with a bit of an emphasis on what's happening in Canada, specifically in regards to rapid prototyping using electron beam lithography. And then I want to talk about the quantum computing efforts that we have here that I just described, and that includes fabrication, tunable lasers, and things like detectors and single photon sources. So silicon photonics, I've been working in this field for about 15 years. Many of you are quite familiar with this area, taking advantage of CMOS manufacturing, all the tools and all the investments that have been made. And we know of companies that are doing quantum computing using silicon photonics. So I think it's widely recognized that this is perhaps one of the best candidates for implementing well, communications, but also quantum computing. So one of the points that I have come to recognize is that working with foundries is wonderful, but we also have a need for rapid prototyping. So a lot of concepts, we don't want to wait a half a year or a year to get chips back. And so we would benefit from rapid prototyping. In terms of applications for silicon photonics, one that we're today is quantum information processing, but there's a whole host of applications that are doing really well, with the telecom and the datacom being the sort of 99% of the market today. And with the pandemic, actually, we're seeing really interesting work in the biophotonics space. So, for example, Genelate has a COVID-19 test that works on a silicon photonics platform. So what I've been up to for the last little while is working on designing photonic circuits and photonic chips. So this is an example of an optical switch network. So this is the idea here is that you can route information, have thousands of switches, and have some flip-chipped electronics to control the whole thing. And so we've been working on fundamental improvements in the devices. So, for example, achieving very high efficiency optical switches. So this is 100 microwatts roughly for a pi phase shift. And devices that can be controlled. So, for example, here's a ring resonator that can be, you can measure its state in terms of where the resonance frequency is and being able to actuate it, and some control electronics to keep everything stable. So this is the kind of projects I've been interested in, is combination of electronics and photonics, and gradually trying to make bigger systems. And what I like about this kind of work is that these large-scale switches are actually very similar to what PsiQuantum and others are doing in the area of quantum computing. So I think there's a lot of overlap in things that can be taken from the classical world and brought to the quantum world. Let me speak a little bit about what silicon foundries are offering and what are doing around the world. So we have a host of research foundries that provide low-volume manufacturing. We have multi-project wafer services that provide access by essentially sharing the costs of the fabrication, and we have high volume fabs. And while we've been really enjoying working with these with foundries, the challenge that we run into is, sometimes you want to have a result back within a week, within maybe next day, within a month. And so this is where we come in. We have this organization that we've created called SciPic Fab, which is focused on fabrication, and we've been working with Applied Nanotools, University of Washington, and UBC, of course, to do some rapid prototyping. So let me describe this rapid prototyping consortium that we have. So this is called SciPic, so Silicon Electronic Photonic Integrated Circuits, with fab for fabrication, funding from the federal government, several university members, and then on the order of 10 or so companies that have joined. On the fabrication side, MPW aggregation, we have design tools, and we have several end users who are essentially the recipients of all the chips that we're making. So where our consortium is today and where it's going, on the left, where we are today, we've essentially been focused on developing kind of standard basic capabilities, such as waveguides for standard telecom wavelengths, and I'll talk about the need for the 2.9 microns when we come back to the selenium atoms. So essentially developing capabilities for these exotic wavelengths, things like grating couplers, edge couplers, heaters, silicon nitride, and also offering fabrication runs. So we're doing bi-monthly fabrication runs, and also having these available publicly through Applied Nanotools. We also do internal runs, and so we've had a couple of runs just in the last few months, specifically for the COVID-19 pandemic. We've been working on some sensor projects, and so this involves defect-mediated detectors. So these are basically silicon detectors that don't need germanium. So on our roadmap, where we're going, superconducting detectors is something that we've demonstrated that we'd like to be able to offer to the community. We have some discussions about germanium, and we have a project on 2D materials integrated with silicon. In modulators, we're exploring some I guess exotic p-n junctions, looking at polymer modulators as well. We have a project on something called photonic wire bonds, and I'll describe that a little bit more. But essentially providing connections between silicon chips and optical fibers, and also connecting to 3.5 chips for things like gain amplifiers and lasers. We also do some CMOS integration. In the context of this talk today, single photon sources detectors are something that the SciPic Fab would like to offer. And ultimately, we want to cover the entire ecosystem from design all the way to packaging of chips. again, in the context of rapid prototyping, slightly more reduced options, but a little bit more flexible. So let me show you some pictures of what this endeavor looks like. So I guess the jewel of our facility is a new electron beam lithography tool. So this is a 200 millimeter tool. It's the latest in Joel's line of machines, and you can see it. You can essentially load either wafers, or you can load 1 square centimeter chips into the machine. And what we like about this machine is that you can actually write waveguides. For example, you can make 200 millimeter long waveguides or 100 millimeter long waveguides. The stitching accuracy is exceptional. We've never actually seen any stitching errors, and so they're definitely less than 10 nanometers. And the write field is 1 millimeter, and it has slightly higher throughput. It is taking a while to write full wafers, so it typically takes about a day to write a full wafer. So what we've been doing with this tool is developing fabrication processes for things like waveguides and directional couplers. And here you can see all the individual shots of the electron beam things. So we're involved at the very low level, optimizing and understanding how you place all your little pixels in order to get the smoothest waveguides. And so a big effort has been to try to minimize the propagation losses, which in electron beam lithography come primarily from the roughness induced by the quantization of the grid of the writing. So we're working on silicon waveguides, we're working on silicon nitride waveguides. And then on top of this base capability, we add other things like doping, etching, suspended structures. So we obviously work on suspended photonic crystals, which I'll talk about. And so some of this allows you to do, for example, thermal isolation. So these are efficient phase shifters. This is quite an interesting device, defect-mediated detector. So basically, just by introducing either dopants or implantation defects, you can create absorption in silicon, and then you can read off the signal from 2 contacts. And so this has been a really nice workhorse for us in terms of trying to build systems that don't require germanium. And it turns out that this structure is not only a detector, but it's also a heater. And so you can do simultaneous heating and detection in the same device. To get light in and out of the chip, we've been using standard sub-wavelength grading couplers, and also sub-wavelength edge couplers. In terms of devices that you can make with these things in small circuits, here's some examples. So filters are a really important component for quantum information, for pump project filters. And so we've been working on Bragg filters, but this is the one that we're most excited as a group, and I'll say a few more words about it. Contradirectional filters with some essentially add drop multiplexers, and using those ring resonators and the defect mediated devices that I was describing here, you can make ring networks. And what's neat about this is that you only need a single electrode per ring resonator in order to both sense and control the ring resonator. So this allows potentially kind of scaling up to large systems. And the largest we've made is I think it's a 16 by 16 matrix of ring resonators using this approach. So a little bit more exotic things that we're adding. So novel materials and devices. I'll talk about the photonic wire bond in a minute. So we have an interest in integrating light sources with our systems. And so this could be things like indium phosphide lasers, but also looking at defects in silicon. So whether they're things like T centers or W centers for the near telecom area, or the selenium that I'll be talking about. We have an effort to try to put these defects in the right place in these cavities, and also make tunable photonic crystal cavities. So this is to couple to these atoms. And at the end, we also need to make detectors to read the signals. And so these are superconducting nanowire detectors, and I'll describe those in a few minutes as well. In terms of test, we do things with probe stations. So we have single chip probe station, we have wafer scale probe stations developed by Professor Reishi's group at Laval and being commercialized. Some rudimentary packaging, just wire bonding, gluing fibers, and then this exotic thing called the photonic wire bond. So let me tell you a little bit about photonic wire bonding. So photonic wire bonding, we actually are getting this machine, very exciting, delivered on Monday. So this has been something that I've been dreaming about for probably about 5 years. Christian Koos's group at KIT has been publishing on this since about 2012. And basically what this technique allows you to do is through 2-photon lithography, perform polymerization of a resist. And wherever your beam is focused and you have a nonlinear 2-photon absorption, you have a much smaller pixel size. And so the pixel size here is on the order of half a micron, maybe a micron or so. And so you can create essentially 3-dimensional structures. Perhaps the most famous one is the 3D picture of the Eiffel Tower. But what's useful for us is to write freeform optical waveguides that make connections between, say, 3-5 chips and silicon chips and glass chips and optical fibers. And so we don't have the tool yet, so we've qualified it. So we've had our own chips packaged by Vanguard, but these are just pictures from publications, just so you get a sense of the kind of things that we should be able to do very, very soon. So our interest with this tool is to be able to offer this to the community. So if anybody is interested in having chips attached to fibers or to lasers, you can get in touch with me and we can explore that. And I guess as part of our consortium that I mentioned, the SciPig Fab Consortium, this is one of the offerings that would be part of that. So if you get a chip, we can also attach optical fibers, and we have an inventory of lasers, and so potentially we should be able to deliver lasers and fibers attached to silicon photonic chips. So I'm very much excited about this. And for quantum information processing, the reason I'm interested in is these losses can be extremely low. I think the world record demonstration with this tool has been under 1 dB for coupling from a laser to a silicon chip. So in the area where every photon counts, I think this is a really exciting opportunity. And I should mention that this has been tested at liquid nitrogen temperatures, and some of the activities that we're going to be planning on doing are to test it at even colder temperatures, just to make sure it works down to the 4 Kelvin for the superconducting detectors. Other activities that we have in our consortium, so SciEpic is a program that has been running since 2007. So we've been doing education in silicon photonics, and this has been primarily working with international foundries. But several years ago, let's see, 2015, we started offering an online course. And this course actually includes fabrication through Applied Nanotools and University of Washington. And so what we do for this course is all the participants in the course actually create a design, we fabricate it, we test it, and we give you experimental results. We've had a little bit of a hiccup in the last few months with the last course that ran, especially with the pandemic, but we do have chips that are currently being measured, and we have a next course coming up in September. And so the way this course works, if anyone's interested, basically we just give you 2 weeks of design time, 2 weeks of layout time, and then you submit your mask. So you have basically 1 month to create your first design, and then you send it off for fabrication, and then you get your measurement results, and then you write them up and compare them to simulation results. Okay, so let me jump into quantum information processing with silicon photonics. And so the starting point, I guess, for this would be to look at what companies like PsiQuantum are doing. So this is a really beautiful picture that illustrates most of the ingredients of what I'm interested in doing. For PsiQuantum, they don't need the cavity QED approach. So this is the linear optical quantum computing approach, where you have single photon sources, you have filters for rejecting the pumps, and you have essentially an arbitrary unitary matrix operation. So this is similar to the interferometers that I was describing at the beginning of the talk in the context of optical switching. Then you have some single photon detectors and some electronic circuitry. And so there's a lot of challenges in this whole thing for the community to work on. Electronics is another one, which is how do you stabilize this entire system? I think that's a really big challenge to figure out, but there's lots of challenges throughout the whole thing. And so I'll speak a little bit about some of those challenges today. So what we're doing is a little different than that. So the Xanadu approach and the PsiQuantum approach involves what are called flying qubits. And so these are photons that are traveling through your circuit, and you perform measurements at the end to perform the calculation. Oh, somebody's got it unmuted here. Maybe if you can mute your microphone. So the disadvantage of the flying qubits approach is that photons don't tend to live for a long time in silicon, even silicon nitride. Typically, it's on the order of picoseconds or nanoseconds. And so this is basically has to do with your dB per centimeter number that you have in your manufacturing process, leads to very short lifetimes. And so if you compare that to ion traps, which are in the minute scale, this is a big challenge. And I'm not sure how easily surmountable it is, but that's the one that keeps me worried is all the losses in the system. So we're constantly working towards reducing optical losses in our silicon photonic chips. What we're doing is a little bit closer to the diamond community, where they're working on nitrogen vacancies, and diamond defects give you spin lifetimes that are on the order of seconds. But the challenge there is, how do you manufacture large-scale diamond systems? That's not really as obvious and not as mature a field. So if you can combine the advantages of the cavity QED approach in diamond, but putting that in the silicon platform, that would be potentially the best candidate. And so Stephanie Simmons' group has discovered essentially the selenium candidate spin in silicon having lifetimes on the order of seconds. And so now these atoms are comparable to the defects in diamond, but they are in silicon. And so potentially the manufacturing approaches in silicon are going to be a lot easier. So there's other important parameters that we have to think about, things like identical qubits. And so this comes from the fact that these are atoms, so they're identical, high fidelity operations. There's already been demonstrations on these selenium qubits from Steph's group. High temperature operation. So these actually operate at relatively high temperatures of several Kelvin. So compared to ion traps or I guess superconducting chips, maybe more specifically, we're not operating at millikelvin temperatures. And compared to things like diamond, there are no interface issues. These atoms are deep in the silicon, really far away from any dephasing issues. So it appears that the selenium in silicon photonics meets all the requirements simultaneously, which is exciting. And so we have a lot of work to do to catch up to everybody else in the world and demonstrate the viability of this proposed platform. So coming back to this picture, again, I want to kind of start describing a little bit more detail of what's happening. We think of injecting light through a grating coupler, then coupling into a photonic crystal cavity. And in the photonic crystal cavity, there would be one of these selenium atoms. And then you're looking at essentially strong coupling between the photonic crystal, the photon, the single photon, and the single atom. And then we perform readout measurements through these other two grating couplers. And a little bit more detail on what the selenium atom looks like. So this is a deep donor. And so what this means is it has a fairly large energy for the transition that we're interested in. And so this is the optical dipole transition is 2.9 microns. And so our photons have to operate at this transition to go from this ground state to the excited state. And the other part that's important is to think about where does the electron qubit live? And so this is going to live in this ground state right here. So there's a spin up and spin down transition here, which is more of a gigahertz kind of level transition. So so those are I guess the relevant energy scales. We've got a dipole transition for optically addressing the qubit, and the qubit itself is spin up, spin down through these two transitions. What's been really impressive about this atom is the T1 lifetimes have been measured to be more than minutes and even several hours, just measured last year. So this is so that's a really impressive number. But more important is the dephasing time. So that's the T2 time was measured. I guess this is already in 2013. Was already measured to be seconds at the temperatures of 1.5 Kelvin. So this is roughly the temperature that we need to be operating the system at to get these long dephasing times. And to create transitions, this is going to be similar to the other schemes in quantum computing. So you're going to use microwave pulses to manipulate individual qubits. And so this allows you to go essentially up from the S state to the T state. So this would be individual microwave pulses. But there's but because of the large binding energy, there's a dipole transition that's on the order of 2 dBi. This is this 2.9 micron. And so this allows you to do a spin qubit readout and potentially qubit interactions as well. So if you want to learn more about the Selenium platform, if you look at Stephanie Simmons on Google Scholar, take a look at these papers. There's a host of papers that describe essentially the details of the materials of these these atoms. And like I said, this work is done by our colleagues at Simon Fraser University. So what we're doing is essentially building photonic crystals this is at 1550 nanometers using 220 nanometer silicon. This is just our starting point, just to make sure we have photonic crystals working. And we're trying to translate these processes into the mid-IR. So now we want to work at 2.9 microns, and we're using thicker silicon. So this is 500 nanometer thick silicon. Same kind of idea, just the dimensions are a little bit larger. And what we're trying to achieve is this strong coupling where you have a high quality factor and a small mode volume. So you have very strong light matter interaction. And we know from our previous work and also other publications that it's possible to get Qs of 1 million and mode volumes on the order of a cubic wavelength. So the calculations based on the dipole transitions, in order to get strong coupling, it would look like this. So this hasn't been done yet. This is what we're trying to demonstrate, is we think you need on the order of 35,000 just to get to strong coupling, perhaps another factor of 10 to be able to do something useful with this. But what the experiment would look like is if you get a coupling of your photon to the atom, then you'll get a splitting of the energies. And so then you should be able to detect essentially whether you have your whether it's a single peak or a double peak. And the way you do these experiments is going back to this picture. You basically just shine light into the cavity, and you will either see a spectrum that looks like the one on the bottom, one of these, and that is an indication of where your qubit is living, whether your qubit is in the excited state or the ground state. So if it's in the ground state and you have a single photon in here, you will get a splitting. And if the electron's in the excited state, then you will not get a splitting, and you will see the single peak. So that's where we're going. That's the direction, and that's the challenge. So I want to speak about what we've been doing to get there. So the first challenge was we don't have any lasers. There are manufacturers who have been trying to make lasers, but they're they don't quite meet the specs of trying to get to very high quality factor measurements. And so for the last maybe 3 years, we've been building lasers. So these are lasers based on nonlinear crystals using one tunable laser, a second single mode laser doing difference frequency generation. And then, so the tunable laser allows you to sweep, and then this PPLN nonlinear crystal, we also have to change the temperature. It's a little bit involved in order to achieve phase matching. But essentially we can get a sweep over a broad enough wavelength range to cover specifically the transition that we're interested in. So the transition I mentioned we're looking at is the 2.9 micron transition. And so, yeah, so we have this laser. I think this has been published maybe at Clio this year, and showing good enough performance in terms of 15 milliwatts of power, and 3 minutes to scan a whole spectrum. So, and then finally we have this coupled to a fiber, so then we can come into our cryostats with an optical fiber and start doing measurements through grating couplers. So some of the early measurements that we've done on cavities, these are the 2.9 microns. You can see 2.9 micron is here, and so here's one cavity that's close to the correct wavelength. The quality factor you can see is still not high enough, so we have some fabrication activities to try to improve that. And you can see that different cavities have resonances a little bit all over the place. And so this is worrisome. If you look at 2.9 microns, 2.98, this is a long way away. And I should come back to this slide here where I didn't mention what is the line width. But the line width of this transition is only on the order of, I think it's 100 megahertz. And I think I probably have that number somewhere in the next slide. So we need to get our cavities to be lined up with our atomic transition. So 100 megahertz atomic line width. And our manufacturing process in silicon photonics, typically, we have a few nanometers of variation in height and width, and that leads to cavities that are anywhere in sort of maybe a range of 1 terahertz. And so the challenge is, can we do 10,000 times better in terms of manufacturing? And I think the answer is probably not. We're investigating lots of post-trimming techniques. That's questionable whether it's scalable. We might get us to the first qubit, but after that, we need some scalable solutions. So what we've been looking at is some kind of dynamic tuning mechanisms. So in the beginning of the talk, I talked about electronics controlling switches
Lucas, it
and
looks
ring
like you have a
resonators.
question there.
Okay,
If you
do you
can
want to
see
read
the
it off?
chat.
I can't,
That's
yeah, I can't
okay.
see
It
the chat.
says, what brand 778 nanometer laser are you using?
Oh gosh, I have absolutely no idea. I could get back to you so if somebody wants to email me, I can
Okay.
send you this paper,
Yeah,
but
that was
I
from Stefan
can't
Preble.
remember.
He'll contact you.
Perfect. Yeah. No. Yeah. So like I said, this was presented at Clio, so we can send you the all the details on how to make that one. But and I could pick one, but it'll probably be the wrong manufacturer, so I don't want to try. Sorry, Stefan. Okay. All right. So I think the challenge is to come up with a tuning mechanism that allows you to be on resonance for eventually we're going to need thousands and millions of these qubits. And so the work that I was describing at the beginning on electronics stabilizing ring resonators, I think is, in my mind, kind of the way to go, is that every qubit will have to have some electrical signal to control it to get matching. Um, and of course, room temperature things are a little bit easier. We have thermal optic effect, that works fine. We have injecting carriers, removing carriers, things like PN junctions. All these things have problems. The temperature effects just don't work. So we've measured very low thermal optic coefficients at 4 Kelvin. So that's not promising. Optical losses from absorption from carriers just seems like a really bad idea. So we're not pursuing that. So the approach that we've been going down is the path of MEMS devices, where we're going to be mechanically tuning the devices. And there's lots of research around the world. There's a whole it's a whole field unto itself. And so we want to take advantage of mechanical structures. So the structure that we've come up with is basically starting off with a conventional photonic crystal. This is an H0 cavity. And by looking at where all the optical fields are in this cavity, you can identify where the field minima are. And it turns out that there's not much electric field in this region which we have drawn. And so we said, okay, well, what if we cut this cavity in this region? By the way, there is a lot of field here and there's a lot of field here. But if you find a region where there's not much light, then you can cut it. And then what we're trying to do is essentially to move these regions, and that essentially changes the effective index of the mode and will result in tuning. And so the challenge here, of course, is that tuning makes sense, but the quality factor is something that's really challenging. And I'll speak about the challenges of how do you make this to be a high-Q device. So so the first thing you can do, this is a comparison of experiments and simulations. The smaller these trenches are, the smaller essentially the perturbation you are on the electric field. And what you can see is that leads to the highest quality factors possible. So from simulations, you can see we can get, in principle, if you get down to close to 0 gaps for these regions, maybe say 5 nanometers, you can see we can get on the order of 1 million Q. So it looks promising, and I'll talk about our efforts. I think we're realistically trying to get to 20 nanometers, and 20 nanometers still gets you above 100,000. So potentially this looks possible from a simulation perspective. Our early experiments were at least an order of magnitude worse, and I'll talk about some of the reasons for that. So the first part is quality factor. I think there's still a lot more room to optimize these structures to figure out better ways of cutting them. And there's a trade-off fundamentally in terms of how much wavelength tuning you're going to get versus how much reduction in quality factor. So for example, we could have cut the structure maybe a few holes away instead of right near the antinode. So if we did this a little further, we would see higher quality factors, but the tuning would be reduced. So it's possible there might be a combination of methods, better fabrication, and then maybe this would be used as a fine tuning. So right now we're starting with a very coarse tuning. As you can see, we're talking about tens of nanometers. So the fabrication, I guess I started off talking about we need rapid prototyping and we need fabrication processes that are better than foundries can offer. My understanding is the best CMOS fabs in silicon photonics can get down to about 60 nanometer feature sizes. And 60 nanometer feature sizes on this graph gets us to not far enough. So this proposal is sort of thinking in the future when we can get to much smaller feature sizes. So you can see we're aiming for 20 nanometers, and we ran into essentially fabrication issues. Just to point out how challenging this is, we're looking at a photoresist or electron resist thickness of 500 nanometers. And in order to etch all the way through a 500 nanometer silicon. So we're looking at an aspect ratio of 500 divided by 20 nanometers. So that's a really high aspect ratio. And you can see in some of our experiments, this is really not working, right? So we're getting little broken things. So a lot of this has been looking at the electron beam lithography details to try to improve and compensate for effects. You can see this hole, for example, is larger. The trenches tend to fill in, and so on. So that was the starting point. Since then, we've made some good progress. So we're working with Genesis and Joel, and looking at a variety of different techniques that are possible to do compensation. So starting with the mask layout, doing modifications to the mask, and doing exposure compensations, taking into account the scattering of the electrons in the exposure. So what you can see is we're looking at long range proximity error correction, short range error correction, and this other approach that Genesis has, which is shape proximity correction, which is essentially modifying the shapes to get what you want. So I think we made some good progress there in terms of trying to get where we're going. There's still a little bit more to go, but we're starting to get to see some positive work here. So where we're at with this, this is a device similar to the one we showed before. You can see the photonic crystal here with a tuning structure, and what we're adding is the mechanical supports around it. And so you can see there's electrical contacts and metallization. And this is using electrostatic actuation to pull or push the structure. So we haven't seen, I guess, excellent results out of the structure yet. So we're still refabricating and optimizing the design, but we've seen a little bit of evidence that there is something happening. So this is a measurement of the output signal. As you modulate the electrical signal, we see some evidence of modulation at the output. But this is still kind of the early days of the structure.
Looks like you have another question here from Matteo Panicietti. Do you want me to read it to you?
Please, yeah.
It says, instead of using photonics crystal structures as the cavity for qubit photon interactions, well, it's QOT interactions, are there any other silicon photonic devices that could act as a high Q cavity?
Yeah, that's a very, very good question. So ring resonators, for example, is what I started the talk off with. The disadvantage of ring resonators are that you have a very large mode volume. So the name of the game in this activity here is not just quality factors. So for example, we've demonstrated in ring resonators quality factors of 3 million, but you simultaneously have to get a small mode volume. And so what you're looking for is a cavity that really confines the light in a small amount of space. So the ideal structure would be a 3-dimensional photonic crystal. That's not practical. 2-dimensional is the next best. The next best after that potentially is a 1-dimensional photonic crystal. And those actually have also very small mode volumes. So there you have confinement from the waveguide. So you have 2-dimensional confinement from the waveguide and 1-dimensional confinement from the photonic crystal. So that gets you to essentially this sort of lambda cubed regime, also with high quality factors. So at Simon Fraser University, there's an effort to create 1-dimensional photonic crystals for the same purpose. There may be other cavities as well, but really the strong index of refraction cavities like photonic crystals or 1D photonic crystals are the ones that give you the best volumetric confinement. If you start thinking about, say, Bragg gratings or ring resonators that are a bit more weakly confined, then you compromise on the mode volume. So yeah, that's the answer to that. Thank you for your question.
So it looks like there was another one. Could the background of the photonic crystal be an electro-optic dye or polymer of some kind instead of an oxide?
Okay, so could the background be something other than oxide? So I should point out that we're actually removing the oxide in these structures. So these are suspended photonic crystals. So what you're seeing here is silicon floating above air, and below that air, there's another layer of silicon. But related to your question about could you use a different material other than oxide, and the polymers in particular are interesting because you can have electro-optic effects. And so I did mention earlier at the beginning of the talk that we're exploring polymers. So potentially there could be a space to put some little blob of polymer somewhere to achieve tuning. So that's definitely an interesting direction to go in. I think there's challenges in terms of materials because we also have to operate at cryogenic temperatures as well. So there's material compatibilities that would come in. But yeah, for these photonic crystals to work well, the best devices have high index contrast. So you have air and air above and below the silicon structure.
So another question here is, what's the overall insertion loss, say from waveguide to waveguide, if you stick in the photonic crystal in the middle?
Yeah, good question. So theoretically, and probably some hero experiments have shown very close to 1. So a photonic crystal is just like a Fabry-Perot cavity, and if you can change essentially the reflectivity and the transmission parameters to get 100% transmission, and that would be the case if you have especially if you have a low quality factor photonic crystal. So if you have a low photonic crystal cavity, and I can go back to this picture right here. So in this example here, you have a waveguide, then you have a side coupling, and then you have this other one. If you bring this waveguide closer and this waveguide closer, then you can get almost 100% transmission. However, we're trying to get to higher quality factors, so we have to back away these waveguides. And so then what you have is a trade-off where as you move away from here, you move the waveguides away, you reduce the coupling efficiency, but then you're improving the quality factor. So I think it's a fairly complicated question and it'll also involve the architecture. I know there's a poster in a previous session of this seminar series looking at architecture questions. So that's one of the parameters that you have to think about, is how much insertion loss can you tolerate, because you'll have a probabilistic gate essentially if you're not sure if the photon's coupling into the cavity or not. Now, from practical perspectives, how good can you make a photonic crystal? That's a whole other story. I didn't mention what I think is our worst problem right now, why we're not getting these quality factors very high. And it's partly because of the scattering. The etching that we're using is actually a deep reactive ion etcher, like a Bosch process, in order to try to get vertical sidewalls. So number one is the sidewalls issue are a problem, and anytime you have loss in the cavity, that'll kill your insertion loss numbers that you're asking about. And the other one is also how vertical the cavity is. It turns out that these cavities are extremely sensitive. What you get is you get polarization conversion. The T mode couples into the TM mode. Even if you have 2 degrees sidewall angle, that results in a lot of loss to a TM mode that radiates away from the structure. So a big effort that we're doing right now is we have a new etcher that has a cryogenic etching capability that can result in very nice vertical, smooth sidewalls that are vertical. So we're just getting started, and we've got some nice pictures. Unfortunately, I didn't have them in the talk here, but so it's a bit of a complicated question. What kind of insertion losses you can achieve really depends on, in principle you can get up to 100%, but that's not going to be very useful. But as a practical device, I don't have a very good answer for where we'll be in terms of the trade-offs. And I think that problem will be the same in the diamond community. So any of the cavity QED approaches will have a similar kind of trade-off. Okay, so another topic, moving on from cavities, is detecting single photons. So this is my collaborative professor, Jeff Young, has been working on detectors for a few years. And so the starting point for all these detectors are you can commercially buy these superconducting niobium nanowire detectors. And the way these work is you have a whole bunch of wire. So this is maybe millimeter long wire, or maybe hundreds of microns of wire. And you shine light on this. And when there's no light, when it's in the dark, this is a superconductor. So all the current flows through the wire. Now, when you hit a photon with it, so now imagine you hit a photon somewhere in your nanowire, then this breaks the superconductivity and it creates essentially a normal metal, which has some resistance to it, and therefore the current will flow through your load resistance. And so what you see in the measurement is a spike at the terminal. So you're driving a small current through this, and then you'll see a blip of a voltage. And typically people make these a few nanometers, 100 nanometers wide, and very long. And so the challenges with this structure is that it's really humongous. You have a huge timing jitter, because depending on where the photon is absorbed, you'll have a different essentially delay time in terms of based on the inductance and so on. And so what Jeff Young has been working on, and we're currently trying to make better versions of this structure and integrate the structure into our other processes and photonic crystals and so on, is a resonator device. And so the idea is you can reduce the length of the metal significantly if you put this in a Fabry-Perot cavity. So the idea here is that this is a one-dimensional photonic crystal, just like somebody was asking earlier. So one-dimensional photonic crystal where most of the light is located right in this small region. And then these wires really just serve as the electrical leads, but all the detection occurs right in this small region. So right away, you'll expect that this will have much better timing jitter. But because the light is already in the waveguide and you can get very high efficiency, so come back to the question of the previous question about how efficiently you can get coupling into a cavity, it turns out that you can get pretty much 100%. So you can design, if you know what your absorption of this material is, you can design your cavity to be a perfect absorber. And so a single photon will come in and it'll always get absorbed by the metal almost 100% of the time. And so the experimental results, where are they here, showed on the order of 96% quantum efficiency. So this is from the waveguide into the photonic crystal, into the detector. And so now you have detectors that are almost 100% efficiency with extremely low dark count rates and very small timing jitter. A lot of the experiments are actually limited by the electronics rather than the device. So that's another part of this project is we're looking at, we need to improve the electronics to really identify what is the true fundamental limit of performance of this structure. But basically, this is better than commercially available detectors. The disadvantage of this structure is that it's a narrow band effect. And so this, the quality factor of the structure is on the order of 1,000-ish or so, or maybe less than 1,000. So, it still works over several nanometers, but it's not a broadband device like these meandering implementations. But that said, we can also in principle think about tuning them so we can make narrowband tunable detectors. And I think these could serve a really nice role at the end of our systems. Okay, so that's that on detectors. The other part of the system that we need are single photon sources. So we're working on two approaches. One is on-demand sources, which I don't have any results to share here. The ones that I'm going to speak a little bit are the more well-known technique. And I know Stefan's here, so Stefan's done a lot of work. So we've been following what he's been doing.
Stefan actually has a question there, I think, on your last slide about the niobium titanium nitride. Was it sputtered?
So these experiments were done with a sputtered wafer. So this is a commercially procured, sputtered everywhere by some other company. We have since then purchased a sputtering tool, and we can do niobium, titanium nitride. We can do a variety of different things. So for the last 2 years or so, we've been doing, or maybe a year actually, we've been doing a lot of material investigations to deposit much thinner regions of much thinner amounts of material, so we can get much lower than nanometers. And probably also more importantly is the width of the previous devices. That the ones that were published were really wide. These were on the order, I think, of 100 nanometers or so. So we're getting that down to the sort of 50-ish nanometers, maybe smaller. So we're currently working on essentially reducing the cross-sectional area of this metal, which we hope will make it work at the 2.9 micron wavelength. But yes, they're sputtered. So that's a AJA sputtering tool is the one we're using for that. Okay, so hello, Stefan. So yeah, so ring resonators. Basically, the concept is you inject light into a grating coupler. High power signal starts generating single photons at some of the side bands of your ring resonator. So let's say we pump it at this point, and we have single photons coming out on the other wavelength. And then what we're doing is we're building on-chip filters to remove the pump. So this is this filter that I was describing is a really beautiful filter. The way it works is you inject light in here. It's a Bragg grating. However, what you'll see is that the Bragg grating is 180 degrees out of phase. You can see in these teeth, because they're out of phase, what it means is that there's actually no light coming back in this waveguide. And if you look at the phase matching condition, there's actually going to be light that couples into the drop port of the waveguide. So you can engineer this, this waveguide system by changing the period and the size of the waveguides to adjust for whatever central wavelength you want and an arbitrary bandwidth. We've been experimentally limited with probably grading coupler because these grading couplers are so close together. We're limited in our extinction ratio right now. So we're on the order of 60 dB extinction ratio. Basically what it means is that if you shine light in here, you always pick up minus 60 dB signal through the other fibers, even if there's no circuit in the way. So that's our noise floor of just light scattering around all over the system. So we're redesigning this system right now to address the coupling challenges using things like edge couplers and grading couplers that are a bit more further spaced apart. But essentially, we're looking at replicating similar to what other people have done, which is ring resonators as pumps, and then these filters to reject the pumps.
Lukas,
okay, so,
I think you had a question from Marek Osinski. Just clarifying, you mean niobium titanium nitride, not nickel titanium nitride. Is that correct?
It's niobium titanium nitride.
But down in your bullets, it looks like nickel. Is that true?
Okay, so that would be, yeah, that's definitely incorrect. Ni is definitely not nickel in here. That should be. Thank you for catching that. That should be Nb. You're right.
Got it.
Instead
thank you, Marek.
Yeah, thank you. Yeah. Thanks, Marek. Okay, so. Yes, okay. So characterization. So we do have single photon detectors in the lab. So we're starting to look at measurements. We don't have single photons yet, but I think we're getting close. And so we've been looking at spontaneous four-wave mixing and stimulated four-wave mixing. I guess another day we'll have some more results hopefully on that, and especially on the newer chip where, yeah, I guess the challenge that we're really running into is in terms of the signals that we're picking up. I think we're limited by the noise of the pump that's not fully being rejected by the chip. So we need essentially, we think the filters are probably good enough. I think it's just the coupling problems that need to be improved. Okay, so let's talk about what I guess my concluding remarks in terms of what we need for silicon photonic based quantum computing. So currently, all the companies in the world that I know of, either continuous variable or linear optic quantum computing, are using flying qubits, and I think there's limitations to that approach, which I have no idea how they're going to fix. So our group has been working on coupling using some sort of quantum memory, and that would be a spin qubit and in silicon ideally. And so the candidate that we're most excited about is the selenium one. I should mention that Steph's group at SFU is also looking at different candidates. So there may be other candidates in silicon as well. So there's a material effort there to try to find the best qubit materials. What we need in general are, and this, I think the first few bullets here apply to linear optic quantum computing, low loss optical components. And so optimization of silicon photonics becomes even more important. And in particular, coupling between fibers and other things like that. So photonic wire bonds, I'm looking forward to working on that. And so if anybody's interested in exploring photonic wire bonds, especially for quantum information applications, send us your samples. We'd love to discuss with you. Probe station, so we're working on a load-locked automated probe station, which will have fiber arrays and automated alignment so we can screen thousands of photonic crystals. And I talked about lasers in here somewhere, single photon detector sources. Tuning techniques I think are going to be really important. So even for the psi-quantum approach, they will definitely need phase shifters and modulators and so on. And how do you do millions of those without dissipating a lot of power and heat in the system? So there's really big challenges there that are exciting. And of course, electronics to control these. On the cavity QED side in silicon, our focus really is on photonic crystals in terms of the etching, in terms of tunable structure, small mode volumes at these exotic wavelengths. And the eventual challenges right now, we can do electron beam lithography for the ion implantation masks or just bulk implantation. And that works fine if you're doing 1 or 2 qubits, but as we eventually get to larger systems, there will need to be techniques for selective and controllable ion implantation. I know there's groups in Australia that have solved or have made progress on that front. And our current challenge, which is, our sort of our 1 year to 5 year goal, is to achieve strong coupling. And we want to demonstrate essentially single photon to single atom and show that splitting that I was describing earlier. So if you want to get in touch with me, there's a few things. I guess I mentioned 2 efforts that we have in British Columbia that I'm involved in. One is the Silicon Photonics program. So this has been running since 2007, training people to do silicon photonics. The other effort is a quantum computing program, combining Microsoft and IBM and D-Wave and 1QBit and Xanadu and all these companies, and training students in software and hardware. And my personal interest is to combine the silicon photonics and the quantum computing and to look at this intersection. And so essentially for the last 3 years, that's been a really big focus. We have a team of about 10 people at UBC and 10 people at Simon Fraser University that are busily working on this. And we'd love to chat with you if you have any interest in discussing. So thank you very much for listening and for joining me.
Okay, I'm going to clap on behalf of all the muted participants. Lukas, thanks very much for an excellent talk. There are a couple new questions here. You might want to click on your chat menu option. Yeah. If you can, there's one from Stefan and then Merrick again.
Okay, so what are you considering for the load lock cryogenic probe station? Okay, so we have a system from a company called Cold Edge. It's a customized system. So we've basically, for the past year or so, we demoed a system that was kind of a standard one that Cold Edge had. And we've been working with a company to essentially customize it and add a load lock module. So there's a valve and there's a load lock unit, and then there's the main chamber. And so the idea is that you put your sample in the load lock, you pump, you have it open up, you leave the base pressure in the chamber, close the lid, pump it down, and then transfer it into the system. And then when you're in the system, then we have a fiber array that's on a XYZ SmartAct controller, and we can do all the same stuff that we do at room temperature. So we can scan, especially at the beginning when all our photonic crystals are all over the place and they're maybe not electrically tuned, we need to find one photonic crystal and a device with a single atom or a few atoms. And so the idea is to be able to do high throughput screening of these devices. So that's what I mean by a question about load lock cryogenic system. So yeah, it's a custom built system. Yeah, if you're interested in finding out more about that, yeah, it's been a really long haul to get to it. Lots of design and so on. Lots of custom parts being built for it, but we should be publishing something about that soon. And we have almost all the parts. I think during this COVID-19 time, we've actually had shipments arriving. So we're just getting back into the lab and starting to assemble things. Marek Koshinski asks, how do you identify the position of the selenium atom? So that's going to be a really difficult one in terms of identifying it. The approach that we think for the near term that we're going to use is, if you look at the antinode in the photonic crystal, the region where you have a high electric field is on the scale of 100 to 200 nanometers. So we have to hit a region about that big. Our electron beam lithography tools, as I showed you, we can pattern down to sort of 20 nanometer regions. So our plan is to create a little mask that's about 20 nanometers in size and hit it within that 200 nanometer window where we need to get the field. So then the next challenge essentially is going to be the Poisson distribution of how many atoms you have implanted. So we're going to do a shower implantation, and that will give you some cavities 0, some cavities 1, some cavities with 2. And I guess we'll do measurements on that and hope for the best. As we start moving into trying to get 2 qubits coupled, the likely approach will be to find qubits that are working and then connect them either with photonic wire bonds or with interferometers throughout the system. And then beyond 2, that's who knows how long from now, infinity away from now. So there's still more work to be figured out there. Okay. What would be the benefit? Don asks about of having room temperature photon number resolving detectors. What would be the benefit of that? Well, okay, so we're using those. We're using commercial detectors right now for that purpose. Room temperature operated with all that. I'm not sure if there's a benefit for it, but I'll speak to why we don't want to use room temperature ones. And the main disadvantage of the room temperature ones would be the coupling efficiency. So coming out of the silicon photonic chip, you lose light, and then in the fiber, and then into another cryostat. So actually our cold edge system, actually we have two chambers right now. We have one chamber for the commercial detectors, and then we connect it with a fiber. But eventually we want to replace, have all the detectors and have hundreds of detectors on the silicon chip to get that nearly 100% quantum efficiency. But then we'd still want all the electronics that that companies like ID Quantique have on photon resolving and timing and all that kind of stuff. Okay, Mateo asks, is it possible to use spins in silicon to create a deterministic 2-bit quantum gate between two flying photonic qubits? I'm not aware of a deterministic gate that can be made. Everything I've been reading about and students have been discussing is everything is non-deterministic. So I would refer you to, probably the better answer would be to talk to anybody who's doing diamond cavity QED. The platform that we're pursuing is exactly the same. And so anybody in the diamond community will probably tell you the answer. And I think the answer is no, but I could be wrong. So if anybody else on the call has a better answer, please feel free to chime in. We've been thinking everything, our architecture has been assuming that it's a non-deterministic gates and that you have to perform. So we're using the so-called measurement-based approach to quantum computing, or one-way quantum computing. This is a technique that was invented by Robert Rosendorf and his colleague. And it's my understanding that this is what PsiQuantum is using, where because everything is non-deterministic, you perform measurements, and the measurements tell you whether something happened or not. So that's the approach that we're pursuing. Okay, so I don't hear any diamond people chiming in, but maybe Don or Stefan, if you can answer that, that'd be great. Okay, the next one is from Shuedong Hu. Could quantum dot spin qubits give you larger spin photon coupling strength? So yes, so quantum dots are maybe could give you larger coupling strength. There's some disadvantages to quantum dot based systems. So one of the key words that I used in the talk was deep donor, and the word deep donor is very different than shallow donor quantum dots. So quantum dots have a very large number of states that are very close apart. So the dipole transitions are close together. And so it wouldn't be very obvious to try to find a dipole transition that's suitable for that kind of work. If you're using an atomic transition, you have these large dipole transitions. So that's the first reason to use an atom instead of a large kind of quasi atom like a quantum dot. There's a few other issues. Interface issues I mentioned as an issue. So these quantum dots typically are at the surface. So there's some possible challenges there. And then the final one would be that quantum dots have this small energy spacing, therefore you require a low temperature operation. So so quantum dots I think maybe are more amenable to microwave cavity QED approaches, and there are definitely lots of groups pursuing quantum dot coupling to photons, but those photons are microwave photons, not optical photons. Okay, Mikhail asks, coupling loss of 1 dB between functional elements of chips sounds not so good for quantum photonics. Are there alternative approaches for where you can achieve ultra low loss coupling? Right, so I'd agree with you that 1 dB doesn't sound good enough. I think I'd also point out that as far as I can tell, everything else I've seen that is practical has worse insertion losses than 1 dB. There may be hero experiments that you can do that get you lower coupling efficiency than that, but if you need hundreds of connections, that'll be a problem. So, in the long term, the way I see this working is that, what most groups right now are doing are having a room temperature silicon photonic chip with optical fiber going to a detector. And so that has these multiple dB coupling efficiency. I think the better solution is to integrate the detectors on chip and have everything on chip. And so then the only thing that we're going to need to provide light for would be, if we're using the heralded photon sources, would be pumping in the pump into the chip. And there you're maybe pumping 10 milliwatts of power. And that loss is not as important. However, you don't want to have tons of light, like in our experiments right now with the grading couplers, that light is just bouncing around everywhere, the extra loss. And so having higher coupling efficiency will mean that we're also minimizing the amount of extra stray light that's generated in the system. So I think, you know, the 1 dB coupling efficiency, I agree with you, may be a challenge for if you want to couple from one chip to another and there's single photons being transmitted. But I also think there's opportunity to bring down that 1 dB further. And so the tool that we're getting, this photonic wire bond tool, I understand that we're going to be the first ones in the world to have that tool outside of the company that has it, which is Vanguard. So our interests are to, you know, can this tool be used for quantum information applications? Can we drive that loss down to even smaller numbers? And some of the HERO experiments showed sort of 0.3 dB. I don't know how much we'll be able to get further. And it also is going to be wavelength dependent. So at 2.9 microns, we have absorption issues with water vapor, and that at the 1310, 1550 might be a bit better. So, yeah, so Mikhail, that's a good question. I'd love to understand your constraints a little bit more in terms of if you can give me a target number, what you think would be good. And I should say that from an architectural perspective, we are including these numbers in our losses to think of what is the qubit fidelity ultimately going to be in an architecture. So, so we're definitely aware of that issue too. So thanks for your question. Okay, looks like
that's about it.
At the end, yeah.
Okay, well, thanks very much, Lucas, once again. And just a reminder, folks, that tomorrow we're continuing our cavalcade of superstars this week. We'll have Dirk England from MIT, and please join us a few minutes early for a word from our sponsors. So long, everyone. Signing off. See you tomorrow.
Thank you very much. Bye-bye.